Okay, so we still have to do a little bit more work to understand how to determine whether critical points and endpoints are maxima or minima. And to finish this point, we will draw again the usual picture of our function f on a bounded interval I, and where we have this I has two endpoints, of course, which are extrema in our case, and as they are always, by the way, endpoints usually are, and plus these three critical points. And so we're still thinking about how to determine which of the critical and endpoints are maxima and minima. And to understand this, first we have to assume something extra, namely that in addition to f being differentiable, we have to assume that the derivative is continuous. Okay, we do so because most of the functions you will consider are so anyway. Now we will make a scheme which you can use, which is very convenient. So we draw the endpoints and the critical points, we put them into the scheme. So we have these 5 points, and on top of the line we put some information on the derivative, and below we put information on f itself, which I will specify now. Now, how can we determine whether this is a maximum? Well, if we would know that the function f would be increasing on the left and decreasing on the right, then it would be clear. So, if we could determine in some way that whether that f is increasing between these points, decreasing between these two, and then increasing again, decreasing, then of course then we would be ready, because if we would have this scheme here, we wouldn't even have to look at our function to see that if it's increasing starting from the left endpoint, it will increase, then the left endpoint must be a minimum. It increases and then decreases, so we have a maximum. It decreases and then increases here, so we have a minimum. Increases, decreasing, we have a maximum here, and it decreasing up to the right endpoint, so we have a minimum over here. So this, if we would be able to complete this scheme, we would be ready. Now, in the same way as we saw that a maximum must be a critical point where the derivative is equal to 0, it's also not hard to derive that increasingness of f in a point means that the derivative is positive, decreasingness that it is negative, etc. Now this, if we know f prime, we can calculate. If we have calculated the critical points, we can also calculate whether between critical points f prime is positive or negative. So this is what we are going to do. We fill in the schedule on the top of the line and then infer the schedule below the line, and then we know about the maxima and the minima. So let me summarize this approach. So this will be in fact the scheme that you will have to use of all these videos. So determine what we should do to determine the maxima and the minima of a function on some bounded interval. Well, you determine the critical points. The endpoints, of course, you know anyway. You make the scheme. And you do the scheme with critical points and endpoints. This scheme is, of course, has the goal to determine the maxima and the minima. We determine the extrema. Well, suppose that you have this scheme. You have completed the scheme on the top. We have, well, again, a number of critical points. I don't know, say 2 endpoints, 3 critical points. Maybe they can, of course, be equal. Some endpoints may be critical points as well. So suppose we found that the derivative is positive between the first endpoint and the first critical point, then again positive in the next, between the next critical points, negative between the critical points following those, and then positive. And then just without having to think very much, we can infer that f is increasing on this first part, increasing in the second, decreasing, and then increasing. And you can complete the picture immediately by realizing that at the left end point, where f is starting to increase, we must have a minimum. Well, here we have a situation where the function remains increasing, so there's no maximum or minimum. So this would be an example of a critical point, which is not a maximum or a minimum, nor a minimum. Here we swap from increasing to decreasing, so we have maximum. Here again we swap from decreasing to increasing, so we have minimum. And so we increase upwards up to the end point, so the end point is a maximum. It's a very easy scheme. And what you now can do, which we didn't discuss earlier, is that we can infer whether, a maximum or minimum is absolute or local. It's just by looking at their values. This is true, by the way, if the interval where we look at is bounded. So we get our conclusions by plugging in the values in the points that we discovered here. And so, for instance, if we know that at these points f has a maximum, and we want to know which one is the global maximum, then you just have to compare the values at these points. There was one remark. Okay, so is this now? Yeah, I wanted to make a remark about the question whether such a situation is possible, that a critical point here is not a maximum or a minimum, and then the simplest example which tells you that this is possible is the function fx equal to x to the power 3, because if you look at the derivative, well, the 3 goes down and the power decreases by 1, so I'm writing error. So you get 3x squared. If you look at the scheme, so what are the critical points? Well, we just don't care now about an interval yet. So f prime x equals 0 if and only if 3x squared equals 0, and this is only true when x equals 0. So x equals 0 is the only critical point. But if you look at the scheme where you put f prime and f at the point 0, then you can see that the derivative is positive because it is equal to 3x squared, and 3x squared is positive everywhere except when x equals 0. So it means that we have indeed this similar situation which I described over here, and we can infer that f is increasing in both of these parts, and we cannot have maximum or minimum at the critical point.